Hey everyone, so welcome to today's video. Today's video will be about implementing discrete Fourier transform using Python. And the sound file that I will implement for the transform is actually me playing piano. It's the recording of me playing the piano music Victory. It's a really nice song and I hope you enjoy it. Alright, so let's begin coding. So first of all, I suggest you create an environment from Anaconda. Uh, yep. So my environment created for this video will be called camp0316. And so once you've done that, create a notebook file and let's begin our coding. So the packages we're going to use are three. So we're going to need NumPy, of course. Wait, sorry. So if you haven't installed it, install it to your environment. So we're going to use NumPy. We're going to use matplotlib. And we're going to use soundfile. So if you haven't installed it, please install it. And because I have installed it, so yeah, I'm just going to skip that part. Right. So let's import our modules. Let's import the library. So import soundfile as SF or NumPy as. And because we're only using the pyplot from matplotlib, so we'll just import the one we need. So as plot. No, yes, right. Okay, so we imported all the stuff. Now let's load our data. So I stored the file, this one, right? Yeah, it's called a master.wav under the soundtrack um under the soundtrack folder. So we're gonna load the file, right? Just to asset for read. Okay. And our frequency. So the frequencies we have once we done our Fourier transform will be mp.fft freq, which is then data times our sample rate. Right. So this basically gets our data and sample rate and our frequencies. Right. It will get these loaded. And now let's define a function to write sound file. So we define the function write sound to be based on this is the right. Yeah, I'm gonna use VAV for my sound file. Okay. Okay, I'm gonna check if this function works by just doing a trivial case for the data I've loaded from a master.wav. I'm just gonna do a trivial one. So it's going to be data sample rate. Let's say call it min. Let's hear it. All right, it works perfect. So yeah, that's our function to write sound file. So now let's get into the Fourier transform part. So let's define our transform of our data into the Fourier domain. We call that x. So let's do our Fourier transform um, for our data. And let's see how our data looks by doing a plot. So we're plotting, so yeah, because now we transformed into our frequency domain. So now we're plotting, our x will be frequencies, and our y will be the Fourier transform. Actually, it will be. Let's consider the magnitude first. Yeah. What is this? Right. So this is basically how our function looks in the Fourier domain. I mean, basically, we're only really interested in this part. Actually, we're only interested in the positive part because the negative part is like it's trivial. So it's the same thing essentially. So let's us restrict our interest to the positive part. So we add a limit from zero. Let's say from 0 to 1,000 first. So yeah, this is what our function in the Fourier space looks like. So you can basically guess that each of these peaks represents the note of the music. Okay. So now I'm going to create a code to consider the only particular frequency. So for example, we want to neglect all the high frequencies. We only want to consider the low frequencies, and then we do an inverse Fourier transform. So suppose I want to get the bass sound for my piano and the pitch, like the high pitch sounds for my piano. So for my piano music, what I can do is that I define a function, restrict frequency. Let me just um next to be freak greater than min freak and freak less than max freak. So xi index equals to 0. So anything that doesn't satisfy our condition will be set equals to 0, right? And then we'll just try actually. Okay. So let's consider our plot again. So just the first plot is just the plotting frequency. Sorry, plot the plot frequency x. Oh no, wait, it's the absolute value. Yep. And if we now consider restrict frequency at mean freak equals to 0, it basically now it only gives the positive part, right? And I think it should be self-evident, right? Actually, why don't I just place a place a plot on top of it? So strict freak, min freak, right? Yeah. So this is our function to extract the frequencies that we're interested in. So now what we're gonna do is that we're going to basically split our music into the low frequency part and the high frequency part. And we're gonna neglect negative frequency because it's very trivial. So what I'm going to do is that our cutoff will be 400. And I'll explain why I set it to be 400 in a bit. Well, it's basically because that if I consider the Fourier space for this C note, the central C note, spirit, yeah, for this note, which is like the middle of which is the middle of your 88 keys piano, right? The Fourier space looks something like this. And like anything, so like its frequency is basically centered about like 400, 500, something like that. So I'll do 400 for my frequency cutoff. So any frequencies less than 400 will be classified as low, and notes with frequency greater than 400 will be classified as high. And now what I can do is that, so I would say low, which to restrict Yeah, because I'm only considering the positive part, so I set mean freq to be 0, max freq to be our cutoff. And for high, I'm gonna restrict. Sorry, equals to. And let me just plot it to verify that if I done it correctly or not. So yeah, so yeah, that's for our low, and for our high, it's basically just yeah, NP absolute value high. Okay, yeah, I think it looks pretty good. So now we can apply our inverse Fourier transform. So say low time. So now we're gonna transfer back from our Fourier domain to the time domain. So we actually get the sound that we're actually hearing. So low time will be NP dot for the inverse Fourier transform of low. And because I usually like if we extract the low sound, the volume is very low, so we have to like scale it. So I'll do a scale factor of 10. Yeah. And for high, will be high. T. Okay. So yep. So now let's replay it. So we write sound. This will be our low. Okay, let's hear it. So it works pretty good, right? It basically extracted like the notes with low frequencies, and we can do the same for high frequency. So if you write sound high time real sample rate, let me call that high, right? Now let's hear this. And let's hear the master sound again, like the combined one without just the our original data. So it's quite evidently that it's actually a mixture of the lower frequency and the higher frequencies. So what we essentially did in this video is that we divided our sound into its lower frequency part and into its high frequency part by considering discrete Fourier transforms. So that's it for today's video, and I hope you enjoy it, and please like and subscribe. Thank you.